Hello everyone, I am Dr. Khan Arif Nafis, currently working as assistant professor in Adama Science and Technology University, Ethiopia. Today I am going to talk and take discuss about the electric field. It is a second slide related to electrostatics. In that, I will start first how we define electric field and how can we get the intensity or strength of electric field at different any point in the electric field and how, what will the formula for electric field intensity due to point charge, and if suppose there is not a single charge but different charges are there, and due to different charges what will be the electric field intensity at some point, or if we want the net force on a point where the test charge is there due to different charges. So by the superposition principle, we can get this. And after that, the electric lines of force, how can we represent the electric field by these electric lines of force, and what their shape and how they appears, and what their the properties of these electric lines of force. So first of all, if we start in our daily life, we have a lot of instruments. Some instruments are they based on electric phenomena, and some are based on magnetic phenomena, and some have electromagnetic phenomena. There are somewhere electromagnetic wave phenomena is used there. Different articles like our mobile phone, our communication system, where we are using electromagnetic waves, some electromagnetic brake and generator, where household generator, where or some other generator, where by the change of magnetic flux we are inducing electromagnetic force, means electricity or electric potential we are using. So lot of instruments based on electric phenomena, magnetic phenomena, or electromagnetic wave phenomena. But if we see what is the basic cause behind these phenomena, so if we see this, basically it is charge. The different situation, different condition of charge give rise to different aspects, and we see, if charge is at rest, so it produces electric field uh, around us. It produces electric field, but no magnetic field. If charge start uniform motion, if it is moving uniformly, the speed is constant, then the resultant consequence is we will get electric field as well as magnetic field. But this electric and magnetic field, they will be constant with the time. And the third condition, if charge is in accelerated motion, then this accelerated motion, the consequence, the result is we will get electric field and magnetic field both. But this field, these are time varying electric and magnetic field. They are changing electric and magnetic field, which are changing with respect to time as well as space. So this leads means changing electric field. In further slides and phenomena we discuss, the changing electric field leads to magnetic field generation, and changing magnetic field generates electric field. And by this way, the disturbance goes up to some distance or some other place, and we can recognize it. This leads this the result is generation of electromagnetic waves. Now, if we define electric field, what is the electric field of a charge? The space around the charge in which if some other charge enters, this charge will experience a force of electrostatic force of attraction or repulsion based on uh, the variety. If this is same kind, then it will be repelled, or if it is opposite type, it will be attracted. So the space around a charge in which when another charge enters, this charge will experience electrostatic force of attraction or repulsion, then this space is known as the electric field of this source charge, where means the space in which the influence of this source charge can be experienced. Now, this influence, this effect of the source charge will not be same at all the places, at all the distances. It will be strong near to the source charge and will be low, less away as we go away from the charge. Now, what is the electric field strength? If in the electric field we want the strength of electric field at some place, then how can we find out? The electric field intensity at any point in the electric field is defined as the force experienced by unit positive charge. Unit positive, if you want the electric field intensity at this point, just place unit positive charge at this place. What is the force experienced by this unit positive charge? That is defined as the electric field intensity. To find out this, we just use a positive test charge, very very small test charge, and we place at that point. And what is the force experienced by this test charge? We will divide by the magnitude of the charge, so we will get the force per unit charge, and that is defined as the electric field intensity at that point. As the by the Coulomb's law, we know that the force experienced by this test charge will be 1 over 4 pi epsilon naught q naught over r square. And if we divide by the q naught, we will get the formula of electric field intensity, that is 1 over 4 pi epsilon naught q over r square. This small r, that is the unit vector, represents the direction of the force. If it is positive, then it will be repelled, and the direction will be this. If it is the source charge is negative, or then it will be the positive test charge will be attracted, and the direction of the force will be in this direction from q naught to q. Here we see that if we are taking positive charge, then the direction of force will be in the direction of electric field. And if the test charge is negative, then the direction of the force will be opposite to the negative charge. And electric field is a vector quantity. And also, if we say about the unit, then SI unit of the electric field is Newton per Coulomb. That is clear from here. E is equal to F upon Q naught. So unit is Newton per Coulomb, or the second unit volt per meter. In next lecture, we'll see how we are getting this another unit of that. Now, if we want to find out this electric field intensity due to point charge, let us consider our source charge is placed as point O. If we suppose it appears as origin, and at the point P, whose coordinates are x, y, z, we want to find out the electric field intensity. For that, we just place the test charge Q naught at this point, and then the force experienced by the Q naught, it will be 1 over 4 pi epsilon naught q naught over r square. If in the terms of position vector, this is the position vector of the point P, R, then it will be 1 over 4 pi epsilon naught q naught r cube into this position vector R. So electric field intensity strength E is equal to F over Q naught, and by this way we will get 1 over 4 pi epsilon naught q over r square. The r cap unit vector just giving the direction of the force or direction of the electric field. Now the superposition principle. This superposition principle, suppose there is not a single charge, but many point charges, discrete charges are there, and due to these charges, we want to find out the net effect at a point. So, at that point, we want to find out the net electric field intensity, or if suppose some charge is there, net force, how much force is there, we use for that superposition principle. Superposition principle says that the net electrostatic force at a particular charge will be equal to the vector sum of individual forces experienced by this charge on which we want to find out the force due to the different individually how much charge it is experiencing due to the other charges. Suppose we can use a test charge, or we can use some other charge. Suppose we want to find out the total charge at the charge Q1. There are many charges q1, q2, q3, q4, q5. Due to all these charges, we want to find out the net force on this charge q1. So for that, we want to find out force on this charge. So total force on the charge q1, that is F1, it will be equal to force sum of all the forces. Force experienced by the charge q1 due to q2, force experienced by 1 by q3, force experienced by the charge q1 by q4, and force experienced by the charge q1 due to q5. And that we can summarize in such formula: Fa will be equal to 1 over 4 pi epsilon naught summation b is equal to 1 to n. How many charges there? Just b will not be equal to a. Means uh, if we are looking it on q1, so the forces will be by the other charges, not by the q1 itself. So it will be given by this charge, this formula. Same thing, the interaction, like suppose we are find out to interaction on some charge. That charge is floating charge, and other will be like a fixed charge, rigid charge. That charge on which we want to find out influence, that is the floating charge. And the other charges will be fixed. And also in superposition principle, we say that the presence of other charges, like presence of charge q3, q5, q4, it will not affect the force applied by q2 on the charge q1. So the presence of other charges will not affect the force on the observed charge by some charge, and their internal forces are also ignored. By this way, we can get the net result on a particular charge about the force due to the other charges, or if net electric field at that point, at some point, due to the different charges. Now, electric lines of force. Electric lines of force, it is a very simple and easy way to represent the electric field in somewhere. This concept is given by Michael Faraday, and if we define, electric lines of force are not real, they are imaginary. Electric lines of force are that imaginary smooth curve drawn in an electric field along which a free, isolated, positive charge moves. So when means these lines, these are not real lines. These, if somewhere electric field, we're not getting the lines there. These are imaginary lines. But the information we are getting by these lines, that are real, that are informative, that informations are real. So we define that electric lines of force are that imaginary smooth curve or straight line, that imaginary smooth curve along which a free, isolated, positive charge moves. Since we are saying that it is free, so it is free to move. And if we see how their shape is, so electric lines of force, if positive charge is there, it looks like electric lines of force are just coming out from there, originate from positive charge. And negative charge is there, so it looks like the electric field lines of force terminate to the negative charge, where the positive charge, it looks like originating from positive charge, and at negative charge they look like terminating at the negative charge. And if there is the charge combination, means positive charge equal and opposite, positive and negative charge equal and opposite charges there, then the shape of the lines is like this. They are lengthwise contracting, longitudinally they are contracting, showing the attraction. And if the similar equal and similar charges there, then the shape will be like this. And laterally they exert pressure, laterally they exert pressure, showing the repulsion between them. And here this n point n, it will be neutral point. Here the electric value of electric field intensity will be 0. If we see the properties of electric lines of force, these are imaginary lines. They originate from positive charge, terminate to the negative charge. The important properties, a tangent drawn at any point on the electric line of force, it gives the direction of electric field. Or if some positive charge is placed at this point P, then the force experienced by this positive charge will be in the direction of the direction of the force will be in the direction of the tangent drawn at that point. And one of the important property of the electric line of force, that the electric lines of force never intersect to each other, because if they intersect, then at the point of intersection we will able to draw two tangents. And that means at the in electric field, at a single point, two directions of the electric field, that is not possible. Every point in electric field has a particular value of electric field intensity and particular direction. So at a single point there are two, means if they are intersecting, then they will imply two direction at a particular point. At a single point, that is not possible. That's why the electric lines of force never intersect to each other. Also, they originate electric phase lines of force originate or terminate normal to the surface. They originate or terminate normally from the conductor. Always they appear coming perpendicular, normal to the surface. And also the density of electric lines of force uh, will will the will be more where the intensity is of the electric field strength is more, and where the electric field is strength is less, the density of electric lines of force will be less. uh, this also, the density is directly proportional to the any point, any place. The density means number of line uh, per unit area. If we held some area, there's how many electric lines are coming out, this is the number of lines per unit area. The density of number of lines will be directly proportional to the strength of the electric field at that point. And also the electric lines of force do not pass through the conductor, means inside the conductor there is no field, no electric field inside the conductor. This is also, suppose some conductor is in between the electric field, by the induction, the free electrons will come this side, positive side, by the induction, and so the lines will terminate here. And on the other side, the by the induction, positive charge will appear, and the electric field line will like originate from there. Inside the conductor, either hollow conductor or solid conductor, conduct it is conductor, so there will be no field, no electric lines of force, and this is known as electrostatic shielding. Means suppose we have some sophisticated and very costly instrument, and we want to save it from a lightning or from some external electric field, then it is very easy to we can do this by putting the our instrument inside a hollow conductor. Then it will be safe from outside electric fields. For example, like we are going by a car somewhere, and in some place, like we are passing through some uh, forest areas there. So uh, all of a sudden, suppose the weather condition is changed, and uh, raining and lightning will start it. So what will be the safest way to save ourselves? Suppose we are looking some houses there, so whether it is good to better to go in house and take shelter, or some big trees there, uh, should we go and stay under that tree, or should we in our car? So it is safest way is just close the windows and doors of the car and sit inside. The car will behave like a hollow conductor, and we will be safe from the lightning and other means spark and other electric shock, because inside there will be no electric field. If suppose some electric lightning coming there, it will go from the outside body to the earth side. That is about the total about today's lecture. In next lecture, next slide, I will discuss something about electric dipole and the electric field generated by the electric dipole in different condition, like in axial point or in on equatorial point. So for today's slide, it is up to this. Okay, thank you.